Okay, welcome again in this class, this lecture. This is the second part of our lectures on communication interfaces. Okay, so at this point we'll be talking about product level or external communication interface. Okay, previously we discussed about the device level, that is the board level, the communication that happens within the embedded board that we are actually considering, the system that we built. So depending on what we want to integrate into the system, we know which of the interfaces to engage at every point in time. Now we want to extend our discussion on trying to connect to the outside world. Now, when we talk about outside world, we are actually talking about the connection beyond the board level. All right. So we're talking about maybe using our device to connect to another device, or using the device to connect to a computer, to a router, to every other thing. What are those alternatives? What are those available alternatives that we can use to initiate communication between our embedded device to with another embedded device, or even with the outside world? Okay, so one, we'll be considering two approaches to communication interfaces. One is the wired communication interfaces that has to do with connections with cables, all right? And then two, we talk about interfaces, interfacing our embedded system with the external world wirelessly, all right? So the wired interface uses is used for data transfer over a wired interface. That's the wired communication interface is actually used to transfer data over a wired interface, whereas wireless communication interface is actually used to transfer without cables. Now, examples of these are the serial cables and USB cables, examples of the cables. And then we'll have also 1394, IEEE 1394 is also a wired interface. That's FireWire. Okay. Now, in the wireless interface, wireless communication interface, we have infrared, Bluetooth, Wi-Fi, Zigbee, GPRS, and so on and so forth. So we are going to be discussing some of these interfaces one after the other. Okay. So the very first one we are considering is the RS232C, which is recommended standard number 232 revision C, and it came right from the Electronic Industry Association. Actually, the RS232C is a legacy device now. What it means is that it's no longer being supported in new machines, all right? So, and it's a full duplex wired asynchronous serial communication interface that extends universal synchronous receiver and transmission communication signal for external data communication. Okay, so when we talk about it's a full duplex, it means that data travels in both directions, even immediately. Data travels in both directions, both forward and reverse direction simultaneously. All right, that's what it means to say that it's actually a full duplex communication. Okay, now when the UART that was actually referenced in this point uses the standard transistor logic, or CMOS logic. It's an extension of this anyway, all right? So, but in this one, the CMOS logic high usually corresponds to a bit value 1 1, and the logic 0 corresponds to logic to bit value of 0. But it is not the same thing in that RS232. So in RS232C, the logic which follows the EIA standard, all right, the logic 0 is actually within this range of voltage. So whenever there is that logic 0 in this particular interface, we are looking at getting this, all right, and whenever there is logic 1, then we are looking at getting negative 3 volts and 25 volts. Okay. Okay, so next we say that RS232 is actually a point-to-point communication interface, and the device involved in RS232 communication are called 1. Data terminal equipment, and then the data communication equipment. Okay, so we see from this picture that we have the data terminal equipment both at the transmitting section and the receiving section. So before we look at this, let's quickly look at the interface itself. So we see from the interface that pin number 1 is called the data carrier detector, DCD, and then the pin number 2 is actually the RXD, and pin number 3 is TXD. All right, that is transmitted data. Then we have the DTR, which is data terminal ready. 5, we have the ground, which is very important. And then at 6, we have the data set ready. At 7, we have the data request to send. We're going to be looking at how these things are engaged. And then we have clear to send and a ring indicator. Okay, so this is a typical interface. This one is DB9 connector. I think there's also a DB25 connector. All right, so when you look at that interface, you can actually look at what each of the pins does. All right, so these interfaces are usually seen at the back of PCs as CPUs. Okay, so if let's look at how this thing works now. So if no data flow control is required that is required for transmission between this and this, now what happens? We say that only the transmitted data, received data, and the ground are required for data transmission and reception. So if we don't even mind about flow control, then nothing spoils. What we do is simply to use these 3 important cables. Okay, so the receiving pin of the data communication equipment should be connected to the transmitting pin of the data transmission equipment. Okay, and vice versa for proper data transmission. So if the hardware data flow control is required for serial transmission, various control lines of the RS232 connections are used appropriately. Okay, so the control signals are implemented mainly for modem communication, and some of them may be irrelevant for other types of devices. Okay, now come to request to send. Request to send and clear to send signals coordinate communication between the DTE and the DCE. How do they do that? In other words, whenever the DTE has a data to send, it activates request to send line. And if the DCE is ready to accept the data, it activates the clear to send line. All right. So the data terminal ready signal is activated by the data terminal equipment when it is ready to accept the data. Okay. Now, the data set ready DSR is activated by the data communication equipment when it is ready for establishing a communication link. Note that the data terminal ready should be in the activated state before the activation of the data set ready. Alright? So the data carrier detect, which is the DCE, the first port or pin. The data carrier ready is used by the DCE to indicate to the DTE that a good signal is being received. Okay, so that is how the function and how the pins relate to each other. So next we look at the universal serial bus. Okay, so we said there's an external bus that allows connection of peripherals like keyboard, mouse, printers, joysticks, and so on and so forth. Okay, it facilitates the data, it facilitates transfer of data at 480, 12, or even 1.5 megabits per second, and it was developed by a special interest group that included several of the big companies that we already know. Okay, the low speed range of the communication using USB is from 10 to 100 kilobits per second and at a 1.5 megabit per second signaling bitrate. Now, at full speed, the transmission is between 500 kilobits to 10 megabits per second with 12 megabits per second signaling rate. Now, when it assumes high speed, the transmission is at 400 megabits and then at 480 megabits signaling rates. Okay. Now, connectors in USB. The connectors in USB are serial A cable and serial B cable. The serial A cable usually connects USB devices to a hub port, whereas serial B cable usually connects detachable devices. Alright, now in networking, okay, the bus topology in networking has different topologies. So USB connects computer to peripheral devices and is ultimately intended to replace all serial ports. And I think it has even replaced it. If there are a few places that serial ports are used, then they are rare. Okay. So in star topology, all devices are linked to a common point, and a common point to refer to as the root hub or the host via the USB. Okay, so the specification as the USB specification allows for connection of up to 16,129 different devices. Now, inside of the USB cable, we have about 4-wire cable that serves as interconnect system, which includes the power line, the ground line, and 2 differential signaling lines. USB also is a pooled device. Now, the USB host is the device that controls entire system, usually a piece of some form, and processes data arriving to and from the USB port. Alright, so sorry, I made a mistake. I said it's a device that controls entire system, usually a PC of some form, and processes data arriving to and from the USB port, and that is the USB host. So it can be a host computer. Alright, now the USB hub, alright, tests for new devices and maintains status information of child devices. Alright, child devices serves as a repeater or boosting strength of up and downstream signals, and it electronically isolates devices from another, allowing an expanded number of devices. Okay, so the next in our communication list, in our wireless communication interface list, is the infrared. Okay, it operates, the infrared actually operates in the region of about 0.7 micrometer to 1 millimeter, all right, in the light spectrum. Okay, so it's just a step up, it's just a one step up on the light spectrum from the visible light. So when you look at the visible light, you see the visible light is in this area. So just before the visible light, you have the infrared region. Okay, this is the visible light region, and when you look at it, this thing is supposed to be 0.7, is it nanometer or so, instead of micrometer. Okay, micrometer. Okay, so that is it. It is supposed to be 0.7 nanometers, that is 700 micrometer also. Okay, so that is it. Most of the thermal radiation emitted by objects near the room temperature is infrared. Okay, so infrared radiation is used in industrial, scientific, and medical applications. Okay, so night vision devices using active near infrared illumination allow people or animals to be observed without the observer being detected. So because of all these things, now embedded system, however, can be designed to perform communication via this. So in embedded system, you can build a security measure around this property of this particular communication interface. All right. So next we look at the Bluetooth. We look at the Bluetooth. So it's a wireless technology standard for short distance exchange. All right, and uses a short wavelength. Is invented by Ericsson, conceived as a wireless alternative to the serial connection, and it uses a radio technology called frequency hopping spread spectrum. Okay, now the Bluetooth device transmits data in packets. So when when you supply data to be transmitted, the system divides it into packets and then transmits each packet on one of the 79 designated Bluetooth channels. So, and each channel has a bandwidth of about 1 megahertz and performs about 800 hops per second with adaptive frequency hopping enabled. Okay. Originally, Gaussian frequency shift keying (GFSK) modulation was the only modulation available for this Bluetooth communication. But since the introduction of Bluetooth 2.0, differential quadrature phase key shifting and ADPSK modulation may also be used between compatible devices. Okay, a master Bluetooth device can communicate with a device of a maximum of 7 devices in a Pi Connect, though not all devices reach this maximum. A Pi Connect, however, is an ad hoc computer network using Bluetooth technology. Okay, the devices can switch roles by agreement, and the slave can become the master. All right, and master can become the slave. Okay, next in our list is the wireless communication interface Wi-Fi. Okay, and the Wi-Fi uses also radio waves to provide wireless high-speed internet and network connections. Okay, Wi-Fi follows the IEEE 802.11 standard and supports internet protocol-based communication. Okay, it requires an intermediate agent called Wi-Fi router or wireless access point to manage the communications. Okay, Wi-Fi will operate basically at 2.4 or 5 gigahertz of radio spectrum, and they coexist with ISM band devices like Bluetooth. A Wi-Fi network is identified with SSID. Okay, and then a device can connect to a Wi-Fi network by selecting the SSID of the network and then by providing the credentials if the network security is enabled. All right, if the network is security enabled. Okay, so Wi-Fi network implements different security mechanisms for authentication and data transfer. All right, so the next in the list is the Zigbee wireless communication interface called the Zigbee, and it's an IEEE 802.15.4 based specification for suite of high-level communication protocol used to create personal area network with small low-power digital radios, such as for home automation, medical device and data collection, and other low-power, low-bandwidth needs. Okay, it's basically designed for small projects. It's basically designed for small projects. Now, in this particular diagram, you'll find that there are three things that are there. Number one is the Zigbee connector. We have the Zigbee router, and then we have the Zigbee end device. Okay, so the Zigbee devices can transmit over long distances by passing data through a mesh network. So basically, the Zigbee devices can travel between 10 to 100 meters. But if they are in a mesh network, you discover that it can travel more than that. Why? Because the information from here, because there's a network, it can pass it to this particular router, or rather pass it to this router, and this router, and this router, and this router. And then before you know it, this Zigbee device has actually sent a message to perhaps this router now, and then this particular Zigbee device. All right, so that is it. Now the Zigbee coordinator will act as the root of the Zigbee network. The Zigbee coordinator will be responsible for initiating the Zigbee network, and it has the capability to store information about the network. Okay, now the Zigbee router is always responsible for passing information from device to another device or to another Zigbee router. Zigbee end device now, talking about the ones in gold. All right, the Zigbee end device containing Zigbee functionality is the end device containing the Zigbee functionality for data communication, and it can only talk to either the Zigbee coordinator or the Zigbee router. So Zigbee end device cannot talk to a fellow Zigbee end device directly. It has to pass through the router as a mediator, or directly to the Zigbee coordinator. So Zigbee supports an operating distance of up to 100 meters at a data rate of 20 to 250 kilobits per second. Then next we look at the GPRS. Now when you look at the GPRS, which stands for General Packet Radio Service, okay, when you look at it, you see that it can as well be incorporated into the embedded system itself. And then this particular system now can now communicate to outside things, maybe my phone. Okay, it can even send another signal to another device, another ES device, that's embedded system device, activating, causing it to do something elsewhere. All right, for instance, if this particular device has a sensor that actually tests humidity level of the soil. Now, this particular GPRS model can be used to send information to another device. And when it sends information to this device, what I'm trying to say in essence is that it must not be phone or any other thing. So when it sends information to this through SMS, now the system has a way of perhaps activating another device, maybe a sprinkler at this point in time. And then the sprinkler will now activate irrigation by the information that this particular one gave. Okay, so a GPRS is a packet-oriented mobile data service on the 2G and 3G cellular communication systems GSM, okay, and was originally standardized by the European Telecommunications Standards Institute. The usage is typically charged based on volume of data transferred. Okay, so there are several capabilities of the GPRS, which when you understand this, you see where you can interface it or use it in your embedded systems project. So next are the GPRS capabilities. Okay, number one is that you can use it to send SMS. All right, you can use it for an always on internet access when you are doing perhaps your IoT. It may not be the best approach, but you can use it to actually do something. Okay, now use it for multimedia messaging service, push to talk over cellular, instant messaging, and so on and so forth. So when you understand these capabilities, you see where you can as well use it for your work. All right, so these are the several communication interfaces that we can have in our embedded system project. Now when you look at the requirements of your embedded system design, it now tells you what interface that you'll be needing, what will you be needing in that particular project so as to achieve the requirement that perhaps your customer gave to you. All right, so this is where we're going to be bringing it to an end. So make sure you're listening very well to your customers and then look at the functionality of what your project will do before embarking on the project. All right, so thank you. See you again in the next lecture. All right, okay.